So today we're going to talk about Chapter 6. Chapter 6 is all about building a confidence interval, which tells us that what we're trying to do is see if we can get the population mean as it's compared with the sample mean. And what I mean by that is we want to know how confident are we that I can look at a small sample and apply it to the population. Remember, a population is an entire group, or a sample is just a piece of that group. So we want to be able to say, how confident am I that my sample is very much like what the population would normally be. So we have to start by defining a couple of things. The first one is a point estimate, and that is a single value estimate for a population parameter. The most unbiased point estimate of a population mean would be the sample mean. So again, we're trying to get the population and the sample to be very indicative of each other. So we want these to be very similar. And how confident are we that what we're looking at really does give us something we can do more with? And if you think about elections, they cannot poll every single person who is electing in that community. So instead, they want to look at just a small sample and make predictions about what the entire community is going to do. So it's very similar with the mean. They want to take a small population mean and see how close that is to representing the population mean. So to start, here is just a point estimate for a population, and it says that we have a researcher who is collecting data. They have a sample of 40 student athletes, and they're looking at the number of hours spent on required athletic activities for 1 week. We want to find the point estimate for the population mean. Therefore, since I'm looking at just a sample, I want to see how close I can get that sample to the actual population. To start with then, we need this point estimate. And basically all the point estimate is the average. So our average we represent as X bar since it's a sample. So this is your average for the sample. And that's found by taking the sum of all of my X values and dividing it by N. So everything that we've done before in the past, nothing new. So I'm going to add up all of these values. If I do that on my calculator, I get 797. The number of people surveyed was 40. So my average is approximately 19.9 hours. So again, I want to see whether or not that 19.9 hours can apply to an entire population, not just to the 40 students that we surveyed. And how close is that? It won't be exact, but it should be able to be getting pretty close. So the next thing we're going to define is an interval estimate. So again, we're estimating. So this now is going to be an interval, or a range of values that we can use to estimate with. And we want to know our level of confidence. How confident are we that my data actually can fit into what I want it to fit into? So how confident am I that these 40 students actually applies to the population? How confident am I that that's going to happen? Okay. To do that, I also need what are called critical values. And these are values that separate sample statistics that are probable from sample statistics that are not probable or unusual. Basically, we're looking at several things. So in this example, I see that C is equal to 90%. That C is your confidence level. All right, so C is this blue area right in here. Okay. To find the area of the yellow, then it's going to be 1 minus C. So if C is equal to 0.9, then 1 minus 0.9 is equal to 0.1, and that's going to be the yellow area, or in my case, the red, since I didn't change pen colors. Okay. Since this combined equals, in this case, 0.1, then that means each one of these little tails individually is equal to 0.05 and 0.05. So collectively it equals 0.1, but individually each tail equals 0.05. Then, based on your critical value, this has to do with your standard normal. And we talked about before in the past how a standard normal curve, 68% of the data is in the center, and then each tail has a certain amount. So basically what we're finding is a critical value. And so CZ is what we call a critical value. And so this critical value is negative because it's to the left of 0. This critical value here is positive because it's to the right of 0. And the best thing you can do is memorize this part, although you can also find it on your standard normal table. But if the area is 90, then my critical value is going to be, the positive one is going to be 1.645. The negative value is going to be the negative 1.645. Luckily for us, we only use about 3 common values. We use the 90%, which is the one we just discussed. We use 95%, and we use 99%. So if you can memorize these values, you won't have to look them up on your table. If you don't have them memorized, then you're going to have to go to where this area is equal to 90 and then find out what your z-score is at that point. And again, that was last lesson, so we've done that before. But our commonly used ones, we have the level of confidence, and the z-score. So again, if you memorize this table, you're going to be in better shape. So we have 90%, which is the one we just looked at, and the positive is 1.645. We do need the negative, so if you want to go ahead and add that to the chart, it would be negative 1.645. To build a 95% level of confidence, my z-score would be 1.96 for the positive and negative 1.96 for the negative. Z-score, negative critical value. And then the third common one that we use is 99%, which the positive one would be 2.575 and the negative one would be the negative 2.575. So again, if you can memorize this, it's better for you. It's not that hard, but you can also always find it if you change the 90%, and make sure you do that. Don't forget that you're looking at 0.90, 0.95, or 0.99 under your table, your standard normal table. So since there is a difference between this, what we call that difference is a sampling error. So this is the sampling error. And again, you may have seen when you look at certain, again, if I go back to the elections, oftentimes it says that this person is up at 10% over the other one, but then it also gives you a plus or minus. So it might say he has a 10% advantage and it's a plus or minus 2%. Basically, that's that sampling error. There's an error that they can't account for, or they do account for, based upon the idea. Again, they're trying to take just a small sample and apply it to everybody, and that's a very difficult thing. So the smaller this error is, the closer we're going to be to what we want to be. All right. So given a level of confidence, C, and remember that's going to be either the 90, the 95, or the 99%. The margin of error, or your error sampling, is labeled as E. Okay, to find your E, this is the formula that you're going to use. That's the formula that you're going to use. We can only use this by now. You should know that there's only certain times you can do these things. And the first one is that the sample has to be random. So we have to have a random sample. And at least one of the following is true. The population is normally distributed. So again, we're looking for that normally distributed, or n is greater than or equal to 30. So that has the two things that you're looking for. If you hear in the problem that it's normally distributed, you don't care what the n value is. If you don't know it's normally distributed, then that n value is important to us. Okay. All right, so finding an error, margin of error. Use the data from the previous example, so that was our athletic data, and a 95% confidence interval to find the margin of error for the mean number of hours spent on the activities by all student athletes in the conference. Assume the population standard deviation is 2.3. All right, so first thing we have to do, we want to make sure that I can use this. So first thing I want to do is know, is the sample random? Is the sample random? So let's go back to our problem before, and it says in our problem that this is a random sample. So it is random. So is the sample random? The answer is yes. That's a good thing. Okay. Then we have to decide, is the population normally distributed, or is n greater than or equal to 30? All right. So again, if we go back up to our problem, it doesn't say anywhere that this is is normally distributed. It doesn't say anywhere that it's normally distributed, but it does say that we have 40 students. So my n is greater than or equal to 30. So n is equal to 40, which is greater than or equal to 30. So that's a good thing. All right. So now that we have concluded that this is true, so this is true, then I know I can find the information that I'm trying to find. And in this case, what I'm trying to find, in case we've forgotten, what I'm trying to find is the margin of error. So I'm trying to find this E. Okay? So to do that, I need several things. I need my critical value, I need my standard deviation, and I need my number, my n. So my C value in this case is 0.95. It's a 95% confidence interval. That's my C value. From the chart above, because I have it memorized, I'm looking at the positive 1.96 and the negative 1.96. In this case, I'm just going to look at the positive one right now. Okay. The 0.95, remember this is given. This is from the table. My standard deviation is equal to 2.3 hours. And again, that was given. Population standard deviation is 2.3 hours. My n is equal to 40. And again, that was also given previously, but it was given to us. Right? So to find E is going to be equal to my ZC, my critical value, multiplied by my standard deviation divided by the square root of n. So E equals 1.96 times 2.3 divided by the square root of 40. Be very careful if you're using your calculator. Be very careful that you're typing this in correctly. This entire part has got to be in parentheses. You have to put the entire part in parentheses or you will get it incorrect. So check on your calculator and make sure that you get an approximate 0.7127 and a bunch of other things. So that means that my error is about 0.7. This is my margin of error. All right. Please check this on your calculator and make sure that you are typing it correctly into your calculator. Right. So what does this mean then? So here's the interpretation. Why do we find this and what does this mean to us? It says you are 95% confident that the margin of error for the population of error for the population mean, so the population average, is about 0.7 hours. So again, if I'm thinking in terms of a margin of error, that means that we think that most student athletes is going to be at the same average, kind of a plus or minus this 0.7 hour. So it's close, plus or minus. And this now is where we start building the actual confidence interval, the actual interval. And what that does is it says, find your mean and subtract E, find your mean and add E, and then your population mean is going to be between these. So I know this is a lot of words. So this is the sample mean. Remember, that's what the X is. The mu is your population mean. So we are trying to determine how close the sample mean is to the actual population mean. We're trying to build an interval that collapses those two things together. Okay? And of course, the more we do this with more samples, the process gets better and better. So as you repeat it a large number of times, your process gets better and better. All right. So let's construct the entire confidence interval. So to do this, to construct this, this is the actual interval. What we need is this formula. So we're going to have x bar minus my E sandwiched between my mu and the x bar plus E. So we're going to need several things. This is what we need. We need, 1, the x bar. X bar, remember, is your average. So add up all the x's, divide by n. you're going to need your little c. This is your percent. That's your confidence confidence level. How confident are you? From C, you need the ZC, which again, this is going to be from the table. You then need to find E. E is what we just found, which says take your critical value, multiply that by your population, in this case standard deviation, divided by the square root of n. And then the last thing you're going to do is create the interval. All right. So for this example, we're going back to the one we already did. So for this example, we know that the x bar was equal to 19.9, and this is from page 1. Okay. The first page of this problem where we started that example. We know that the C is equal to the 0.95. We know ZC is equal to 1.96. And again, this is what we just did. We also know that the E value is 0.7 from the above problem. So now we're putting it all together, and we're going to build a confidence interval, which says x bar minus my E is going to sandwich, or is less than, my mu, and then the x bar plus E. So it's going to sandwich it together. So I have 19.9 minus 0.7 is less than the mu, and then the 19.9 plus the 0.7. So if I subtract these two numbers, I get 19.2 is less than my mu. If I add these two numbers, I get 20.6. So basically, this is an interval. My mu is right here at 19.9. My lower end of my interval is 19.2. My upper end is the 20.6. And that tells me that I am 95% confident that this is going to fall in here. This is actually my x bar right here. But I'm going to explain to that when we do the interpretation. So basically, this is what we're doing. It says, with 95% confidence, you can say that the population mean which is your mu, number of hours, is between 19.2 and 20.6. So again, this is your x bar, and we're saying that the x bar of 19.9 guarantees me that somewhere in this interval my mu is going to fall. So mu will fall here. Somewhere in this interval is where your mu will fall. Remembering again, your mu is your population mean. Okay. And again, one more time, just in case. Therefore, it says we can use a sample mean, which is x bar, and apply it to an entire population. So that's huge. We're taking a very small sample of only 40 students, and we're going to compare that and have that apply to the entire population. So it's a small number of items, a small sample, and it's going to be able to be applied to the entire population. All right, so I'm going to stop here at this example, and I'm going to leave it blank for you to try on your own. All right. Before we can do anything, I'll set it up a little bit for you. So, a college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9. From past studies, the standard deviation is 1.5 years. The population is normally distributed. Construct a 99% confidence interval of the population mean age. Okay, so first, I have to check my conditions. First, I have to check the conditions. So first, I have to check the conditions. By that I mean, first condition, is this a random sample? Is the sample random? Is the sample random? And so if I look back at my problem, is the sample random? And it says right here, its sample is random. So we can check that box. That's a check. It's a yes. The second thing is n greater than or equal to 30, or the population normally distributed. So I have to check that one. It's an or statement. Distributed. It's an or statement. So again, if I look back at my problem, it says that n in this case is only 20. So this is a no. That's a no. But it does tell me that the population is normally distributed. So in this case, this is a yes. So it checks. So now I can do the process. Okay. So it's okay to use my formula. And then the process. So what we're after here is my ZC, my E, and then my confidence interval. So you need, this is step one, we need to find the X bar. So how do you do that? You need to find what the n value is. What is that n value? You need to find the standard deviation. You need to find the C value. Then you need to find the critical C, the C critical value. All right. So this one is going to take a little bit of work. You're going to have to add and divide. This one, we already know what the n value is, so that's an easy one. We're also given the standard deviation. We're given the C. So you have to find this one. And then you're going to have to use the table to find the C value. Okay. Step two is going to be to find E. To find E. So the formula for finding E, just to recall, your formula to find your E value is going to be to take, so we're going to use the formula, E equals my critical value multiplied by my standard deviation divided by the square root of n. So you tell me what E is equal to. And then the third thing we're going to do is build the interval. And remember, you do that by taking your x bar, subtracting your e-value, sandwiching your mu in between the x bar, and adding your e-value. So finish the interval. Okay. Once you've done that, then I'm going to move that down just a little bit. So once you find that value, then I want you to interpret. And I want you to do the interpretation. What is the interpretation? Okay. All right. And then one last thing to note here. Just a quick note so that you can see why the interval is important. Okay. So a quick note. It says, since your ZC changes, so it's based on your confidence, it's going to change the E value, then your interval will narrow, so you'll have a smaller interval, or it will widen. So either your interval will narrow, get smaller, or it will widen and get a little bigger. The smaller the confidence is, the smaller the interval. The smaller the confidence, the smaller your interval will be. So if you want to be more confident, then you're going to have to make the interval bigger. If you want to make it more confident that you're getting the results you want, then you're going to have to make the interval bigger. So more confident means we're going to have a wider interval. Okay. All right, so you finish this example on your own. You finish constructing all of the things that we need to construct, and we're going to move to the next one. Finding a minimum sample size to make your estimate. So this is going to tell us how many do we need? What is the minimum sample that we need? To do that, here's my formula. All right. It also says if n is not a whole number, then round up to the next whole number. Because remember, you're looking at a sample size, and sampling typically is by people, and you can't have half a person. All right. So you want to make sure that you are rounding up, no matter what it is. You're going to round up. Okay. So this is just telling us how big should your sample size be? How large a sample do you need? We know that we are concerned with having at least 30, but what happens if it's not randomly distributed? How do we make that happen? Okay. All right. So the researcher in example 1 wants to estimate the mean number of hours spent on required athletic activities by all student athletes in the conference. How many student athletes must be included if the sample for a 95% confident falls within 1 or half hour of the population mean? All right. So we want to know how many athletes do we have to include to be 95% confident within half an hour of each other. All right. So again, just so that you're understanding what we're trying to do here, again, we can't survey the entire population. You can't survey the entire population. That's the problem. We can't survey the entire population. Right? So, since we can't survey the entire population, how many, so how many do we need to survey? For our results to be confident, how many do we need to survey so the sample can apply to the population? How many do we need to apply to the population? Again, think about voting. You cannot survey everyone who is going to vote. So how many do you need to sample so you can make the best prediction for the election? Okay? So my formula says N is equal to my ZC score, so my critical value, times my population standard deviation, divided by E, and then squared. So N is equal to, okay, we're looking at a 95% confidence, so that's 0.95, which means my ZC is equal to 1.96. Okay. My theta, my standard deviation is equal to 2.3. Again, this is from above. Remember, we're using the same example throughout this entire section. So it was 2.3 from the above. And my E this time is equal to 2.5. And that was given to us. So N is equal to 1.96 times 2.3 divided by 0.5 squared. Now notice again, this is a lot of movement to use on your calculator correctly. If you don't know how to correctly input this in your calculator, just be very, very careful. You can also do it in stages. And so remember, order of operations says I'm going to do what's inside the brackets first. So 1.96 times 2.3, I can multiply that first. 1.96 times 2.3 is equal to 4.508 divided by 0.5, and then I'll square it. So if I take the 4.508 and divide it by 0.5, then I get, if I can do it correctly on the calculator, then I get 9.016. 9.016. And then finally, if I square that, I get a long number. So I get 81.288 blah, blah, blah. Remembering that we're always going to round up. So I'm going to round up to 82 students need surveyed. $82 students needing surveyed. And that's going to wrap up section 6.1. Make sure you can use your calculator. And again, if you can memorize this chart, then it's going to help it go a little smoother for you. If you don't memorize this chart, that's fine. You can still find that by looking at your standard normal table. Remembering that this is the area. So this column represents the area. All right.